Okay, I'm trying to figure out the recording, so just wait a minute. Okay. Well, I still have difficulty get the recording going, so well, there will not be any recording today. I will keep trying in the future. Um, Different from last semester is that the Google disabled uh, the the function of recording, session recording in, yeah, just starting this year. So so yeah, that's the problem. I know it used to be that you can always look at the recordings after the class, but this time that may not work. So we'll go along with the slides, and the slides will be uploaded right after the class. So just see, um, try to follow along. Well, fortunately, I think most of you have heard most of the material. Um, Not exactly, but most related materials we're going to cover today with the topic of supervised learning. The reason is that we will start the semester with a project on supervised learning. So we're going to get a little bit of quick overview, not much on specific algorithms, but just the concepts and some tools that I want you to incorporate in your project. Okay, so a little bit later, I'm going to introduce and go through the description of the project. For the time being, we'll start with the introduction of some of the topics of supervised learning. Yeah, if you have seen like some of the slides, it seem similar because I have offered them to other professors to use in the classes. So yeah, if that's the case, that will be easy for you because you know what's already in there. So supervised learning, there are two types of tasks: classification and regression. The difference is on what's the expected output. Either classification or regression both involve some input-output mapping, which we're going to talk about. Yeah, it's like a function. A classifier acts like a function. Given an input, which is a vector, it can produce an output. Okay, the output can be scalar or vector, can be numerical or categorical. Okay, if it's a category, it's considered a classifier. If it's just a number in some continuous range, it's a regression problem. Um, there are some algorithms in supervised learning can work in both. Okay, and some of them are just specifically used for classification. We're going to focus more on classification for this project. So to build a classification model, there are two approaches. Okay, and usually people use those two terms and divide the classification methods called the generative models and discriminative models. Okay, that depends on how much you use to describe the individual classes. For generative models, the idea is that you try to figure out what each class should be like. So you build models of the individual classes. And then for each new sample, you try to compare it with those models and assign it to the class that's most similar or most compatible. Uh, Examples are the classifiers based on some probabilistic distribution, like Bayesian classifiers and their derivatives. Okay. And also, indirectly, like k-nearest neighbor, it's also a classifier of a generative model, although you do not actually generate some mathematical model. Yeah, but basically, it's an approximation of the probabilistic distribution of the classes. The other type is called the discriminative model. And those are models that directly look for some boundary between the classes. Okay, yeah, you do not try to figure out what the classes look like themselves. You just look for boundaries. Okay, as long as the boundary work with your existing data, they are good. Okay. Yeah, and there are many methods that directly look for the boundaries. The simple one, like logistic regression, which by itself is a linear classifier, or simple vector machines or decision trees. Okay, they are all belong to this kind of models. Okay, and very quickly we go through the steps of supervised learning. Basically, you need training data. Okay, training data are those come with the correct answers, or we call them ground truths, or if they are class, they correspond to particular classes, then we call them class labels. Okay. So for the training process, what you do is to feed the classifier with your training data, and you try to modify that function f. Okay, remember we have a mapping. Okay, you try to modify it so that it will approximate the output of the correct answers. So you repeat the process and you try to optimize your model based on your training data. And finally, when you're satisfied, you can actually use it on new data, which is a process called the testing. Yeah. And to build a supervised learning model, usually there are a few steps. First, you need to select a model type. Okay, there are many choices. Okay, some are for regression, like polynomials or mixture of Gaussians. Okay, some are discriminative models, including neural networks. Okay. And for each model type, there are some design choices. Those choices usually are not easily optimized automatically, so you have to decide on them first before you can actually train the model. Okay, like for polynomial, its degree is a design choice. Things like this are usually called hyperparameters. And then once you have decided on the model type and the design choice or the hyperparameters, there are still some other parameters that you can directly optimize. For example, the coefficients of a polynomial. Now, we want to get to the topic related to generalization, and we want to introduce the idea of bias variance dilemma. This dilemma is a dilemma in supervised learning. That means how much you want your training data to fit or to precisely reproduce the expected or the target output. Okay. Bias means the difference between the prediction and the correct answers or the targets. Okay. Low bias means is for the training data, your model can predict the output very well with very little deviation. Okay, so we certainly like to have low bias. However, we also want to have confidence in the output, and that's about the low variance. Because to train a model, because you use training data to build a model, okay, to optimize the parameters. So the actual model depends on the training data you use. Okay. And the training data you can use is just a subset or a sampled set from the actual distribution of all the of that problem. Okay. It's a small subset. So each time you sample that to get your training data, sample from the actual distribution to get your training data, you're going to get a different model, okay, because the model is data dependent. And since they are not exactly the same, there will be variance among the models built with different subsets of your training data. Each time you sample, you do some sampling to get your training data, right? And build a model. There will be some difference. And that difference is the variance here. So to be confident that your model actually works well, not just memorize the training data, but it can generalize well, and it's not too sensitive to which subset of the training data you're using. Okay. You want to be confident of that. That means you want to have a low variance. Yeah, like if you repeat the process many times and the performance is all similar, then you have high confidence that the performance is true, not just some good luck. Okay. This is low variance. So both bias and variance, we want them to be low. Yeah. However, it's a dilemma because usually if you try to really minimize one, you're going to increase the other. Usually to reduce bias, you want to more complex models. Okay, yeah, but this can lead to overfitting, yeah, because you can learn both signal noise. To reduce noise, to reduce variance, okay, then you don't want to learn too much noise because the variance comes from the noise because the training samples always come with some noise. So you use less complex models, and that can be underfitting, which a term means that you do not learn enough to describe the actual distribution of the data. So a very easy way to visualize this is via a regression problem. And this is an example of polynomial regression of some several points that come with noise, and we approximate it with polynomials different degrees. Okay, degrees from 0 to 5, and the bias is actually smaller and smaller. Okay, that's a larger bias because the prediction, which is that straight line here, horizontal line here, is very far from the samples, which are the small circles. And for the last one, the prediction really passes through the samples. Yeah, but this shape or behavior can be quite strange. Yeah, that's because of overfitting. You get a small bias, but it will be very large variance because if I just sample the underlying function, which is the dashed curve here, I sample it again, get a new set of points. You're going to get something really different from this. Okay, that's high variance. So we need to control both, and we want to get the most reasonable one. So what do we do now? Several approaches. Yeah, you can have a number of training samples, or you can try to determine the suitable level of model complexity. And there are more specific techniques. One is called regularization. It's the suppression of model complexity during training. That means you can build a more complex model, and but you build in mechanisms that penalize complexity during the training process. The other is consensus-based methods. Okay, if if you have many classifier, you can like have them vote. Okay, it will average out the noise. Okay, this averaging process naturally reduces variance, but the expected bias is not affected. So usually consensus-based methods is good if you have the time and resource to build the consensus, the ensemble. So we're going to go through all of this. For amount of training data, well, usually when we talk about training data, is the more the better. Generally speaking, that's the case. But there are two limitations. One is the availability. Okay? Some data sources are just very scarce. The other is the computational cost, because you need a lot of resource to process a huge amount of data. In the old days, people are usually more worried about a small set of data. Okay? Yeah, you don't have enough training samples, and you try to do inference and the training from those small set of samples. Used to be the problem, okay, but today it's easier to get large data sets and or huge data set, gigantic data set. Okay. Yeah, and in that case, management of that data set becomes a challenge. Okay. So in some of the algorithms, it's an issue like how do you do distributed training? Okay. When the data set kind of located at many different sites. That's a newer problem. Okay. The next point is about how to generate artificially new data. If you only have a small amount of data, but they do not appear to be sufficient for your training, yeah, but you cannot actually collect more. So you try to produce extra training samples from your existing ones. That's usually called data augmentation. You do some modifications, some perturbance of the existing data to produce new ones, which you still have the confident like target output or confident class label. Or resampling sometimes refer to some combination of training samples. Okay. You consider your samples to be come from distribution. So you think some kind of combination or interpolation of some of them of the same class can give you new samples. That is actually quite common practice, particularly when you have imbalanced data sets, which means that one class may have a lot of data, but there are another class that you just don't have sufficient data. So you want to make more of those to have them more balanced. So you try to resample some kind of interpolation of the training samples from that what you call a minor class. Yeah, you try to make it somewhat bigger. Yeah, so these are all techniques that we can use if we just don't have enough data. Regularization is a process of you basically adding some term into your training objective, like this. Okay. This is a typical objective of polynomial regression. Okay, so that's the output. That's the target output. Okay, that's the predicted output from your polynomial. Okay, and those AKs are the coefficients. And this is a term that penalizes the complexity. Okay. But this is a very simple one. But this form can be used in a lot of similar objective functions, like using a neural network or something like that. Okay, that's okay. So the regularization has the effect that if some coefficient is not that important, okay, this term in the minimization process, because this is the loss function, okay, so it's a minimization process, it will drive that term towards zero. Okay. If a coefficient becomes zero, that basically means a term is removed from your model, so it makes the model less complex. That's the idea of regularization. So this is called an L2 regularization because it's squared. It's like L2 norm. Okay, if you collect the coefficients as a vector. Another very common one is L1 normalization, regularization. In L1 regularization, the square term is replaced with square absolute value. Okay, yeah, it's absolute value. Yeah. And they basically have they both can suppress complexity, but somewhat have different characteristics. The L1 regularization usually has a more or stronger suppression of an important coefficient. So the resulting model is more, I should say, less complex, yeah, than one that you can obtain with that L2 regularization. Okay. And also here, there's another hyperparameter that will come in here, the lambda, which just another way to control the strength of this term. If lambda is zero, then you don't have regularization at all. So that's something you can play with. And the consensus-based methods, yeah. To have consensus, you need an ensemble. Yeah, so you can build many classifiers. Usually just many classifiers of the same type, but train in some different with, for example, with different data sets. So you try to have them to vote. Okay. There are different ways of doing the voting. Some are unweighted, like equal voting, and some are weighted. Okay, and you can assign weights to different parts of the ensemble. And you can build experts. Okay, expert means that it focuses on some region or some part of the input space. Okay, so the weighting can depend on the input, where in the input feature space of the sample. Depends on the input. There are many different ways to do ensembles. But basically, you let the individual ones collaborate to make a decision. So usually to do an ensemble of classifiers, each member of the ensemble need to be simple enough. Okay, so usually you combine simple models or models that are very easy to process, fast to process, to build an ensemble instead of huge ones. Okay, if you have a really big, like a deep neural network model, usually you don't do ensemble of that because it itself is too big. Okay, yeah. However, the most famous one is probably the random forest, okay, which is equal voting ensemble. Because decision trees can be processed real quickly. Okay, so you can have hundreds of thousands of trees to build a forest. And usually the results are more reliable than simply using trees, even complex trees. So how to make ensembles, the members of the ensembles? Okay, usually there are two ways. Okay, because they have to be different. Okay, although you have the same common training set, yeah, and they all come from the same set of data, but they have to be different. So when building the individual members of an ensemble, you need to add some variation or diversity in there. Generally, one is the selection of different attributes or features. Okay. The other is resampling. Okay. It's resampling called bootstrapping, which is resampling with replacement. Okay. That means like if you have a bag of some marbles and maybe two different colors, or say ping pong balls, okay, and you want to sample from there, okay. Each time you pick one, you have to put it back. That means the next sample comes from the same distribution. So that's called the sampling with replacement, or usually is the term that's called bootstrapping. Okay. You can repeat this process many times. So each member of your ensemble will come from a different subset, sampled subset of your original training data. And that brings the diversity. So for the next one, which we're going to cover a little bit more, because the objective here is to introduce cross-validation, which I really want you to have in your project. Okay. Cross-validation is important. Of course, you may already know that already. Okay. The first idea is that why validation data? Validation data is something that you divide as part from the training set. You keep it aside for you to estimate how well the training model can generalize to new data. Okay. So it's used to validate the training process. Usually it's used in the selection of hyperparameters, but you can also use this to compare different classifiers. This is the idea of validation data. Okay, you divide the labeled data into training and validation subset. Usually, when you do the training or with models of different complexity, okay, more complex ones lead to overfitting, so it can get the training subset modeled better. Okay, that difference is what bias. So the bias can become lower and lower. Okay, yeah. However, for the validation, this is when overfitting occurs. Okay, yeah. So what you want is some level of complexity where the performance on the validation subset is optimal. If you have a huge amount of data, then you can just use randomly select some of them as the validation subset, yeah, and you can just go with those. However, if the data do not appear to be sufficient, okay, and most of the time that's the case, and you have the time to do multiple rounds, then cross-validation will give you a better picture. So the idea of cross-validation, I'll just use this for the explanation. The idea of cross-validation is to divide all the data into multiple subsets, and you repeat some process called trials. In each trial, choose one part as the validation subset, okay, the yellow one. Okay, and the others we call the estimation subset, which are actually used in training the parameters or the coefficients of your model. Okay. You repeat the process multiple times, so that means you have to spend more time, and this is just for the selection of model complexity. Think about that. So cross-validation is actually lots of work for the computer. But by doing this, you actually use every sample in your data set once for the validation purpose. The number of trials is called the number of fault in cross-validation. So in this case, it's called the four-fold cross-validation. Okay. So you repeat the process but you don't just use one of those models. Okay, it's not really meaningful to compare the performance of those because it's just the difference. Okay, maybe one of them just get a simpler subset, and one of them just get a more difficult subset for the validation purpose. So it's not meaningful to do the comparison, but we need to combine their results into a single set, single collection. And if one out is used when there's extremely small number of data training samples. Like if you have just 5 samples, then you repeat it 5 times. Each one just keep 1 sample as validation. That's called leave one out. Okay. So I usually use this example polynomial regression to demonstrate the working of cross validation. So in this sample, there are 9 points. Okay, 9 training samples from second degree polynomial. Okay, some noise is added, and I randomly divide the 9 samples into 3 groups. Okay, the cross validation markers 1, 2, and 3. So in this process, okay, I just check the different polynomial orders here, and for each time, for each of them, I have to do the training. Okay, here that means the regression, okay, polynomial regression with a specific order for the training subset. Okay, so just 2 out of the 3 groups I use as training subset and 1 used for validation. So I repeat the process so many times, and then for each of these here, each row is a different degree or more general, a different hyperparameter or design choice. For that, I add the results. Here means all the error together. Okay. For polynomial regression, the common error is the mean squared error. So I just add the mean square error, all of them. Okay. Yeah, just take that. All 9 samples counted here. And I repeat that for all the different hyperparameters, and then choose the one that gives me the best result, which is the example here, second degree polynomial. Okay. Then with the hyperparameter determined this way, you come back to your data. Okay. And use the whole training set to build the model with the selected hyperparameter. And remember this, because I was usually asked by students about, oh, I have for the 4 models here, which one should I choose? So this, you don't choose one of these. Okay, this just let you choose the hyperparameter, and then you use that hyperparameter and all your training sample to train a new one. That one should be used during the testing process. That's cross validation. Okay, I'm going to be a little bit faster today. If you have whatever question, or do you feel it's too fast? Because I kind of think these are not exactly brand new stuff for you. So we'll just quickly go through those. Yeah. If you feel it's too fast, just write something in the message board. Okay. And I will stop and see what we can do. So down to some other topics. One is look at features. Features are very important. Usually we talk about samples, but how are the samples represented by your model or your computer? Okay. each sample has to be represented by some feature. Okay. So features can be numbers or they can be categories, but it's a representation, and the regression or classification is done based on the features. Okay. So features are very domain specific. Okay. Each different domain of problems have their useful features. I'm showing here the very famous iris data set with some features. Okay, this data set has 150 samples for the classification of the iris flowers into three types. Okay, and there are 4 features used. Okay, so for each flower, um, there are 4 numbers. Okay, that number replaces the picture of the flower. Okay, and those are measured sepal length and the sepal width and petal length and petal width in centimeters. Well, we're not going to really get into this data set. Yeah, but this is just idea, very simple, and that's the traditional way. You try to identify features that you think will be useful for your particular problem. For example, in this case, the color is not used a feature. Okay, the color, of course, are characteristics or attributes of the flowers, but they may not be so useful for this classification problem, so they're not included here. But they may be useful for other problems. So the person doing the classification modeling has to decide on what features to use, and that's a big topic. Realistically, you have to think for whatever problems. Yeah, you have to think for the features. A lot of time you have to ask some experts. Like if I am a computer scientist and I have a project of classifying the flowers, I have to ask those familiar with flowers who are the experts to tell me how do they tell the difference between different types of iris. Okay, and then I design the features according to that. Okay. Of course, we can always have the raw features, that's image pixel values. Those are the raw features. Yeah. Oh, I just take, instead of the measured features, I take, that's a picture. And there are a finite number of pixels with RGB values. So those are the raw features. But raw features are more difficult to use. Sometimes because there are just too many values, or you cannot tell the correlation, or whether some values are just useless. There are very many examples here. So usually you have to find ways to identify likely useful features. Okay. And many of those are just derived features from the raw features. For example, you take an image and you compute the average color. That's a derived feature. The example here are just a list of some features that have been used for an important medical problem, which is to do the white blood cell counting. Yeah. Because people in our blood, there's dozens of different types of blood cells, and their ratio and the count is important to diagnosis. Okay. So you have to do that. Yeah. For example, those are just some example features that have been used. Okay. Their size, the shape, or texture features. This is another important feature, which for human detection in images. It's particularly famous because before CNN comes along, that's the state of the art. Okay. And this feature called histogram of oriented gradients, from the picture, of course, you can see those are the gradients. Okay. So it characterizes the distribution of directions of edges and those things. And to combine them, like some distribution like this, that actually looks like a person, right? May or may not be a person, but it does look like a person. That's a set of features. In the days of development of this field, which we call the pattern recognition, good features kind of have more contribution than good classifiers. Of course, there are many, many different types of classifiers. Okay, some are very simple or very straightforward. Some are more sophisticated. Yeah. However, for many data sets, the performance between them are not that different. Okay. Yeah, there may be some difference, but not huge difference. However, different features. Yeah. For example, if I look for different features to do a person, to decide whether that region contains a person. Okay. What features I design has more, I should say, has more effect. Okay. Good features have more contributions than classifiers, the good classifiers, okay, for many practical problems. Okay. So features has been the bottleneck in the development. Okay. People try to design better and better features over the years. Okay, and they are, yeah, think about the bottleneck. Okay. So this is the standard approach. You have the raw data, and if the raw data has too many values, like image pixels, okay, you try to derive or design features, and so you extract more informative but fewer values from your raw data. Okay, very important. Fewer, so you can handle them, and more informative. Okay, so they're useful for whatever you want to do. Some famous features, hard features for face detection, HLG for, which is previous slide for pedestrian detection, back of words for text. Those are all some very representative ones. Before we start for the break, I'm going to go through the two slides here. Yeah, because it leads to why today's model is different. When we look at the most typical neural network based on the CNN, the convolutional neural network. Okay, yeah, the limitation for the what we people call the handcrafted features. Okay, is that they are just limited. Okay, yeah, can capture some useful information, but not all the useful information. And usually they can only represent low-level information. Okay. It's very difficult to design features that can represent high-level information. Yeah, because that's also usually a combination of low-level features, and it makes more and more difficult to work with. Okay. Yeah, just like this. An example is like this. Oh, this looks like a shape, but the features are just local gradients. Okay, those are local gradients. When we look at this, we as human viewer can see that shape. That shape, like, oh, that's head. Head is should be above legs. Okay, generally, yeah, that's some high-level feature that human can understand and grasp very quickly. But it's very difficult to design model for that, design features to model this. Yeah, particularly because there are more diversity, more variation among the high-level features. Okay. So the success of the convolutional neural networks come from the fact that it itself acts a feature extractor. Okay. So instead of the handcrafted features, it directly learns what features it wants to use. Okay. So the networks combine the feature extractor and the classifier itself into a single model. That's how it works and has worked very well. So that's an example that you can find that illustrate the different level of features that can be extracted from convolutional neural networks. Okay. Those are really low-level features, very similar to what you get with HOG. Okay, just different orientations of edges or some like the average intensity, for example. And they are combined to meet their feature, and the high-level features, you can pretty much see what you want to see, very specific to the class of object. Okay, yeah. So that's the idea. Yeah, we need to understand. Originally, people do feature and do classifier, and CNNs do feature and classifier all together. Okay, yeah, and that is the huge step that leads to today's success today. Yeah, we're going to take to save time. I'm going to take just a 5-minute break here, and we will continue at 2:20. Yeah, whatever problem, if you want to ask questions, you can post in the message board. Um, for today's class, I'm going to start at about 3 o'clock because I have a subsequent meeting right after that. So I'm trying to go quickly if possible. And I want to leave some time for explaining about the first project. Okay, first project start today, and it will be posted after the class on E3. So let's start. Well, we have just talked about features. If we just use raw features without the feature extraction, usually the dimensionality is very large. And even if we use the derived features, uh, it can still be quite large, although not as large. For example, if for the image, in the image features like HOG, the histogram of related gradients, the number of features usually around a few hundred. That's still a lot. Okay. So people have thought about the dimensionality reduction, and the most common one is the principal component analysis, called PCA. The original idea that we want dimensionality reduction is come from something called the curse of dimensionality. Particularly in generative models, for generative models, you want to build some description of a particular class. For those descriptions, the number of samples for you to build a reasonable description grows, I should say, exponentially with the dimension. Okay, so to have high dimensional features is actually a pretty large problem. Okay, some students ask about whether slides can be updated before class. Yeah, of course, generally true. Yeah, they will just kind of when I have enough time to do that. Okay, yeah, but generally that will be the case. Maybe if you don't mind, I will spend 1 minute to place it on E3. Okay.
喂，
Yes. Yeah, I'm just trying to upload. Okay. Okay, now we'll continue. So with the principal component analysis, the idea is to have projection to a lower dimensional space, and the projection is linear. So it's like when you write it down, it's usually from space that's X, or the original samples represented as vectors projected by projection um, matrix to another transformed space Y. Okay, so each vector is mapped to another vector. The original idea in PCA is that we want to decorrelate the features. So you try to make the correlation, okay, which is the expected value of this, okay, to be 0. Yeah. So something like this, if we have samples like this, okay, yeah, in 2 dimensions, and we try to find the principal components like this. Okay. For the top view, the 2 dimensions are highly correlated. Okay. So in some way, there's some redundancy in terms of the information they can carry. Okay, so after this projection, okay, actually that's a principal component. The idea is that along this, you actually decorrelate the features after this transform. Okay, so here one is along this direction, the other is along the perpendicular direction. Okay. And for dimensionality reduction, you can get a pretty good approximation if this is a direction that come with a large correlation in the original space. Okay. If that projection actually along this line is very good approximation of the original point. Following this, there are a few pages of mathematics. Okay. If you cannot follow along that well, it's okay. But generally, it's just some proof of the technique people use with PCA for the purpose of dimensionality reduction. Okay. It starts with the idea that the covariance matrix, okay, the terms, the off-diagonal terms represent the correlation between the features or the dimensions. So what we want to do is to diagonalize this covariance matrix. And this covariance matrix is symmetric and we call it a positive definite. So you can always diagonalize it using its eigenvectors. And the eigenvectors are orthogonal. So this sigma x is the covariance before the transformation, and sigma y is the covariance after the transformation. Yeah. Of course, they can, if we just think about it as a decorrelation, the process of decorrelation, they have the same dimensions, but the sigma y, if the A consists of the eigenvectors, okay, then sigma y is diagonal. So there's no correlation between the features after this transform. Yeah. But there is something else. If we want to talk about dimensionality reduction, the idea is that we skip some of the dimensions. That means we make the sigma y smaller than sigma x. Okay. That way, we can have fewer dimensions with this the PCA. And for this, we only have the problem of how to choose which dimensions to keep. So here is a little bit of derivation to prove that we choose this based on the eigenvalues. So it starts with the definition of a data approximation. Okay, the projection, because we have decided that A should consist of the eigenvectors. So the projections are all on the eigenvectors. So that some the projection will be like this. Okay, those are the eigenvectors. And they want to minimize the difference from the original value. That's a projection. That's original. And there can be some derivation with the gradient. Okay, solve all those to minimize that gradient, we get the eigenvalue problem. Okay, and that's putting this back in the original here. This is what we get. Okay, so this is something we want to minimize. And this is a fixed value because it's just the sum of the square of all the samples. Okay, yeah, the norm of all the samples. Okay, so the larger the lambda, the sum of the lambda, which are actually the eigenvalues. Okay, because you have this, so you know that those lambdas that are gradient multipliers are just the eigenvalues. So the larger the eigenvalue, the smaller j. Okay. If you keep everything, okay, then j is 0. So the idea is that if you want to just keep a subset, not all the dimensions, you keep those with large eigenvalues. So that's the idea when PCA is used for dimensionality reduction. Okay. So usually the eigenvalue corresponds to variance along a direction, and the larger variance usually considered as a more useful feature. Okay. And that correspond to that dimension will correspond to larger eigenvalues. Okay. Yeah, so I think I'll skip this step because we have talked about it, and that's just an example for this kind of data distribution. Okay, there are 8 points here. Okay, 8. Each column vector is a point. Okay, you get eigenvalue of 38 and 2, which are just the variance along the 2 directions. Okay. Yeah, those lines you see here are the eigenvectors multiplied by length. The length is the square root of the eigenvalue. Then we're going to have an example called eigenface, okay, which eigenvalue of the faces as face images actually. The face images as the raw data. Okay. So there's no derived features here, just use the pixel values as input. So here are some examples of 40 by 40 face images. There are 200 of them, have males, have females. Okay, and since they are 40 by 4, so the dimensionality is 1600, okay, for each sample. Each pixel is 1 dimension. So with some derivation, okay, there's some trick here because you have more dimensions than samples. So if you just try to do the original PCA here, you will find you have only 400 non-zero eigenvalue. But you have to do the eigenvalue problem on a 1600 by 1600 matrix. Okay, yeah. But you waste that because its rank will be at most at 400. Okay, so there's some trick that to convert it to a 400 by 400 matrix, which is this, and you do the PCA on that. Okay, these two sets of PCAs will have the same eigenvalues, right? And the same eigenvalue, so you can choose the same set of dimensions. So here is a typical plot when people talk about PCAs, accumulated variance or the accumulated eigenvalues. Okay, that's 100%. of all the eigenvalues. And for the first few features, for example, somewhere around 20 here, you already have 80% of the total variance. Okay. For the sum of the 20 largest eigenvalues will be 80% of the sum of all the eigenvalues. So for this, we can see that information is highly concentrated among the first few eigenvalues. That's a projection of the samples along the first two dimensions. Okay. After the transformation, the first two principal components. And, those are reconstruction. Okay. The top row are the examples of the eigenfaces, which are the first few eigenvectors, and you put them back into 40 by 40 images that look like those. Okay, those are the principal components, the first 6 of them. Okay, and that's reconstruction along the first dimension. Now you can see that the larger variation occur from female to male if you look at this, from one side to the other side, which is something quite interesting. Okay. Now, for the rest of this class, I'll go through a little bit about evaluation, because that will be a big part of your project. Okay. For classifiers, usually we think about accuracy. But accuracy does not tell all the story. Because each class can be quite different in terms of the size, the distribution, etc. So usually we want more information, and the basic one is called the confusion matrix. It divides the correct result and incorrect results into different categories and put them in the matrix. So it's like the element ij is the number of samples. Okay, actually that's the ith class, but it's classified into the race class. Okay, yeah. The diagonal ones are the correct ones. Okay, but different type. Okay, that's correct is class 1, predicted is also class 1. Okay, so different correct results and different mistakes. Okay. The off diagonal ones are the wrong results. Yeah. So this is just some other example of confusion matrix. Okay. This is one confusion matrix, a typical one that comes from the iris data set. You can see that it's quite easy to have really good results. Okay. For this one, there are only 4 incorrect ones out of the 150 samples. Okay. And that's another example which has more classes because it want to characterize colors, the color of a person's clothing. Okay. Yeah. So again, the diagonal one is the correct ones, and the off diagonal ones are wrong ones. So those are just some quick examples. Usually for really multi-class problems, we it's best to present whole confusion matrix. However, a lot of classification problems are basically a 2-class problem with the characteristic of yes-no problem, that you want to decide whether something is present or something has occurred. Okay, yeah, something is there or not. That's a yes-no problem. For that, you have usually called the positive class and the negative class, or a true class and false class. Yeah, that kind of 2 by 2 confusion matrix represents something like that. So that's true negative, false positive, false negative, and true positives. And from there, from all those 4 values, there are many different ways to extract two values. Usually, two values come in pairs. Okay, two values or two measures for comparing classifiers. Okay, for example, PD, that's probability of correct detection. Okay, yeah, it's just how the ratio of true positive samples that can be identified or predicted as positive. Okay, yeah, so false negative contain samples that are actually positive. I do this right. Yeah. Okay. Ground truth is positive, predict negative. So those are false negatives. Okay. So PD and FA. Okay. FA is usually called false alarm. Those are pair. Recall and precision is usually also a very common pair, usually used in some retrieval problems or detection problems. Sensitivity and specificity, also in similar scenarios or diagnostic problems, and the PPV and NPV. Okay, the names are here. Okay, you can some of them are just the same thing with different names. Okay, because those are usually used in more of the medical field. Okay, so usually to do the comparison, you need to report the values in pairs. However, although this gives you more information, comparing them in pairs do not tell you which one is better or which one is worse, because usually when one is better, like in a pair, like recall and precision, when you increase recall, usually precision drops. Okay, so if you have two classifiers, one has better recall and the other has better precision, it's hard to tell which one to choose. Okay, so there are some ways to try to combine pair features, and the most common one is called F1 measure, which is actually the harmonic mean. Okay. Its equation is this: is a harmonic mean of precision and recall. Okay. So you have one single value that allows you to do comparisons between classifier or between some settings or choice of hyperparameters. The other one to talk about is the ROC curve. The name is receiver operating characteristics. Okay. It's a product of PD versus FA at different threshold bias values. Okay. Yeah. The idea of that threshold bias is like you can adjust the sensitivity. Even if you have a classifier, you can adjust the sensitivity when it's making the decision. Okay. Of what's called the positive and what's called the negative. So instead of a single pair values, you have a whole series of pair values at different thresholds. Okay. So those are the two extreme cases. Okay. Two extreme ends. One is to call everything false. Calling everything false is here. Calling everything, or I should say negative. When you call every sample negative is here. When you call every sample positive is here. Okay. So if the everything is perfect prediction, then that's that point. Okay. Everything correct. So usually what compare is called the AUC, okay, or area under curve. The larger the curve, the area, the better. So comparison with the AUC kind of separate the choice of threshold and the choice of the classifier or classifier setting or hyperparameter. Yeah, you try to separate these two different things. This is the threshold or bias independent comparison. Yeah, this is one illustration of how you actually build a ROC curve. The final two slides is about how you do evaluation when you have cross-validation. If the evaluation is based on confusion matrix itself, what you do is to combine the confusion matrix of the validation subset in all the trials in the cross-validation, and you add them together. You get a single confusion matrix. With that confusion matrix, you can do whatever you want to compute, like P and FA and procedural recall and F1 and all those things. So it's not that useful or meaningful to report confusion matrix on those matrices for the individual rounds in cross-validation. You just combine them all and give the overall values. The other is about how to do that when you want to plot the ROC curve and to compute AUC. Method one is to just do the ROC curve for the individual ones, or you just combine all the outputs, without considering their individual threshold choices, and just combine all the outputs and draw a single ROC curve. The second one is to use fixed FA value. So you sample at fixed FA, that's the horizontal axis here, and for different rounds, you get different PD values, so you can get an error bar here. For this method, what you do is you fix the thresholds, because to draw the ROC curve, you need to vary the threshold. So you sample among a set of fixed values of thresholds, and at that time you compute the FA and PD for all the trial rounds. So that's way you get the error bars in both directions. So there's no single way of which one is correct, but there are possible ways to present the ROC curve with cross-validation. Yeah, so this ends today's lecture, which may be many slices, but yeah, just want to really get through it once so that we can talk about the project. Yeah, you may notice that I have not talked about any particular classifier, because, well, there are so many of them, and that's not the main objective of this class. So we'll just go with this set of slides, and you definitely should have learned some classifiers in the past, in past courses, and those are sufficient for doing the project. The objective is not to teach you new classifiers in this case anyway. So for the final 10 minutes here, I'm going to switch to the project explanation. Okay, I think you should be able to see it now. This project we have, that's all 3 weeks because that's Sunday. Yeah, but this is an individual project, and in 2 weeks we're going to talk about the game project, which are group projects, so they are kind of separate things. Yeah. The idea here for this project, if for you to actually go through the process to do experiments and write a report that explain your experiments. So the focus is not on the implementation, although a little bit of implementation is still needed. Okay, but there's very little you have to do. Yeah, maybe there's even some tools. Some of you might know this better than I do. Yeah, yeah, but there are some like GUI tools where you can just use and run all the experiments. That's okay. Yeah, the focus for this project is not for you to write programs to do all the classifiers yourself. Although if you want to do that, that's nice, and there's no problem with that. Okay. So we're going to talk about the requirements. Okay. The first requirements is the biggest one actually, is the data set. Because I want you to do experiments on multiple data sets, and one of those has to be a self-made data set. That is not, it does not come from any existing source. I want you to build one yourself. Okay. It can be a small data set, but try to build one. Like if you want to make a data set that, for example, distinguish between two kinds of apples. Yeah, just for example. Yeah. Or yeah, there are many options that you can do. Yeah, just use a little bit of creativity. For example, I was thinking about to tell the gender of, yeah, not general human face, but some comic human face. Faces that you will get in anime or those kind of places. Okay. Yeah. Do gender classification or age classification of this. So there are many things that you can try, do something that's interesting. Yeah, or those are for images, but you are not limited to images, and you can, like the iris data set, you can just try to derive some features yourself. Yeah, or you can, for images, you can use, there are many feature extractors, or for example, like text. If you want to do text classification, okay, yeah, there are feature extractor, that's back of words, yeah, for text. There are libraries you can use. Many of the libraries are like in Python, but C++ also available as well. Okay, if you like to work with sound, some little sound clips. Okay, I used to have some project about like clips that be 2 or 3 seconds long, and you want to do some classification on those. There are sound features. Okay. Many of those. Yeah. So those are, I'm going to talk about the self data first because it's a bigger part of challenge if you want to think about that. Okay. So to build a data set, you need to do the labeling yourself. We're talking about classification. Okay. And also because of the time limit, you should do something that does not require huge amount of data to produce reasonable results. Okay. Most of the time, goal is like 100 or a few hundreds samples at most, unless you find some way to automatically extract a bigger amount of data. Yeah, but you want to be able to do the labeling confidently. Okay, yeah, unless you have access to some experts in some very specific field. Okay, yeah. So think about something that you can build your data set and try to do some experiments. Build the data set, do some analysis of it yourself. Yeah. Some of you might have an undergraduate project on some topic like that. And if you want to use those, that will be okay, actually. Yeah. And if you want to have a few of you forming a group and build a common data set that each one of you can use, that's okay too. But you have to indicate those in your report. And if several of you work on the same self-made data set, I would expect the data set to be better quality and maybe larger in size. Okay, because that's a lot of effort usually put into this. Okay. Okay. So those are the data sets, and for your data set, you need to have a very clear description about how you get the data set, the composition, your source, how do you select them? Okay, because they are usually something that are skipped. Okay, you do not just blindly pick anything you find. How to do the data inclusion? Okay, and how do you do the labeling? Okay, those are actually quite important things because today's machine learning models, people have noticed that a lot of things depend on the training data. Okay, if there's problem in the training data, then there's problem in the result. Yeah, because all the models are data dependent. Okay. So a responsible way is to clearly indicate and spread how your data set is composed. Okay. That's very important. Okay. And other than this, I want you to try some public data sets. Okay, and one of them for image data set. Anything that's image, small image is okay, even if the image is like 10 by 10 or 20 by 20. Okay, as long as that data set is suitable for classification. Okay. And there's also non-image data set. Okay. For this, I usually refer to data set that already come in features. They are already feature vectors or values. So you may or may not see the raw data format. Okay, those are usually already extract features. So for that, you just try to work on the classifier itself. You just try to work classifier itself without worrying about uh, the original data type or worry about processing the raw data. So there are some links or suggestions about where to find some of those data sets. Okay, you just check them out. I will allow Kaggle data sets or data sets from whatever other projects you have worked on. Okay, the rest are simpler. Okay, for algorithms, then I mean classifiers. Okay. Try 4 of them, but I do not require you to code them yourself. Yeah. So those are more for comparisons. And because I want you to try different types. So yeah, particularly if you have gone through the course of Introduction to Machine Learning, which I expect you do, okay, yeah, you probably know more than those 4 types of classifiers. So just choose which 4 you want to use, um, and you can use whatever existing libraries. There are libraries like OpenCV or the scikit-learn, which may be the most well-known library for that. Okay, just use from there. That's all good. Okay, yeah. So that should save a lot of debugging for your time. Yeah, I'm not going to worry too much, and I don't want you to worry too much about debugging your classifier. Yeah, particularly if you work on a neural network and I ask you to implement, for example, all the backpropagation stuff. Okay, my experience is that debugging those take a lot of time and effort and might not be successful. So here, just try some different methods and choose what you want. Use existing implementations Okay, things you can find on the web or some toolboxes. So that saves you for the debugging of those things. And I want you to focus on the analysis. Okay, so that this part, okay. The reporting of your results, you have to think about how to report them. Should be complete or meaningful. Okay, yeah. Things that you should talk about. Like I want you to work on cross validation. Yeah, and use cross validation to compare those metrics where you can compare the different classifiers or different hyperparameters of the same classifier. Okay, and some other things to experiment with, like different amount of training data. Okay, change them by order of magnitude. Like if you have 10,000 samples, you can try 10 samples, 100 samples, 1,000 samples, and 10,000 samples. Yeah, see the result difference. Yeah, you might get some idea about the critical amount of training data that you need for that particular problem. Sometimes you need to try, if you want to do subsampling, try it like a few times, resample it a few times. Yeah, we have talked about the variance in the concept of bias variance dilemma. Okay, that variance thing. Yeah, try to do some analysis of that variance. Yeah. Of course, compare different classifiers and different hyperparameters of the same classifier. Okay. Also, you can try to see the effect of PCA. Okay. You already got some features, and you can see if you use just original set of features, or you do the PCA for the dimensional reduction first. Yeah, for example, the face images. Okay, from that 1600 dimension, you may drop to 10 dimensions or 50 dimensions. How do they affect your results? Okay, and of course, you can play with a little bit of data augmentation. Yeah, particularly for image data. Okay. Also, compare the values, the results. Okay, the public data sets usually come with some places where you can find the common results. Yeah, some data sets have some very well known, like how well they can be classified. Okay, like the iris data set, yeah, it's something about 90 to 95% for the most common classifiers. So if you just get a 60%, then yeah, that's something weird. Okay, yeah, try to do some comparisons. Yeah, it can be expected or explained, but you need to try to do that. Yeah, think about why. Why? And sometimes for some data sets, one classifier may work better than the other, and for the other data set, it's the other way around. Try to do some explanation, thinking about those things. Okay. Yeah, those are all things that you can discuss. Yeah, in your report. So those are the big part. So that's about this project. Um, for the report is a major part. You can see that the coding in this project is not that big a deal. Okay, so it's a report that's important. I'll limit the report of maximum 10 pages single spaced. Yeah, so you do not just list a lot of things and into 20 or 30 pages. Yeah, you have to think about how to organize your report, what to put in there and what not to put in there. Yeah, try to organize your results in tables. Yeah. I don't like students to just copy paste some screenshots. Okay, it's very hard to read. Because usually I will read your reports myself. So use tables to organize your result. Submit through E3, single file only. Yeah, don't submit your code as separate files. Yeah, let submission 3 days. Yeah, is 10% deduction per day. However, you should still include your code after your report, but in the file. Okay, the code, if any, this should still be some. Okay, does not count towards the 10-page limit. Programming language, C++ or Python, only the two, so that we can more easily read those. We will not run your code in general, but we'll still look at those too, particularly if we want to understand what happened. Yeah. So any question here for the report? If you don't have other questions, we will stop today's class here. And yeah, if you want to ask in the message board, you can leave your message. Your question is message board. Otherwise, I'm just going to post this program project today. Okay, so you can start working on it as soon as possible. Yeah, there won't be that much lectures in this course, and we won't have lecture on Friday anyway. So you can just focus on doing the experiments. Okay, and if you don't have any other questions, you can leave now. No problem with that.哎，
那个请问教授听得到吗？
有 ，yes。
那个我想要问一下，就是作业要求有提到用4种演算法，是指说针对每一个 data set 都要用4种吗？还是总共用4种就可以？
对，总共用4种就可以。如果每种都太多的话，有太多的分析，但总要有一些重复的可以比较。
了解。好，谢谢教授。